Good afternoon and welcome everyone. For those of you that do not know me, I'm Cynthia Hernandez, President of the Hispanic Heritage Group. Thank you for joining the Hispanic Heritage Group today to mark the occasion of Hispanic Heritage Month. We are so very pleased to have our speaker, Professor Luz Martinez-Miranda, here with us to share her story of science exploration and perseverance. This is the first event hosted by the Hispanic Heritage Group in quite some time, and I could not think of a better way to reintroduce our employee resource group to Brookhaven Lab. Hispanic heritage is a wonderful thing. It embodies the strength of diversity even within its own community. The Hispanic culture is the most diverse culture you might ever encounter, as we're a mix of European, African, and Native American people and cultures. Every culture in Latin America has its own cuisine, stories, traditions, and styles. But we're united by the Spanish language, and especially by the warmth of our cultures. No matter where you encounter Hispanic cultures, every event includes food, music, and family. And even that definition is inclusive, because to us, family is not just parents and children, or aunts, uncles, and cousins. It's everybody. It's people who are not actually related to you. Your friends become your family, and your parents' friends become your family. I tell you, when you're trying to do the family tree in school, you have a serious challenge. You ask yourself, how are those tios and tias really related to me? How do I fit Cousin Dune into my family tree? Regardless of the differences in music and style, the strong family values in Hispanic cultures remain the same. I think I see some similarities in our Brookhaven Lab culture as well. Here at the lab, we look out for one another, we care about each other, we keep each other safe, and we cheer each other's successes. This is the right environment for the Hispanic Heritage Group to thrive. So please join us. Sign-up sheets are at the table by the doors where you walked in. As I said a moment ago, we're so pleased that Professor Luz Martinez-Miranda has chosen to spend her day with us here at Brookhaven Lab. There's a lot to learn from her, and I'm especially eager to hear her talk. But first, here to introduce Professor Martinez-Miranda is someone who can speak about her impressive career in science much better than me, Brookhaven Laboratory Director, June Gibbs.
Good afternoon, everybody. It's a great pleasure for me to be here, to welcome all of you, and also to welcome you to this Hispanic Heritage Group event, which is the first in some years, as I understand, and which is a great pleasure for us as part of the laboratory to support and to help push forward, one we're strongly encouraging. That's part of a larger effort of the lab and its commitment to inclusion and diversity broadly, the commitment to ERGs in particular. But more generally, as you've heard me say before, inclusive, diverse groups are better able to attack the problems, the complex problems that we face as a nation going forward, especially in STEM. So I&D is a core value at Brookhaven. Safety is also a core value at Brookhaven, as you've heard me say many times before, and as I've started saying recently, we're seeing an uptick in our injuries. They have to do largely with awareness, going to and coming from jobs, so I just want to call everyone's attention to the importance of staying aware, both before a job and after it, as well as during, in order that we don't have any serious injuries at Brookhaven. It's a real pleasure to introduce Professor Luz Martinez-Miranda to Brookhaven. In fact, as you may be able to tell, she has visited here many times before, and back in the old days when I was working at the NSLS, so was she. So it's a pleasure to welcome Luz back to the laboratory. She obtained her BS and MS degrees from the University of Puerto Rico, BS in physics and music, MS in physics, right? And then PhD from MIT in physics. She subsequently did a postdoc at UC Berkeley and then joined the University of Maryland as a professor in material science and engineering, where she has been ever since. At Maryland, she's also a member of the Maryland Nano Center. Luz has dedicated much of her career to studying liquid crystals, both from a fundamental perspective as well as applications and engineering perspectives. Her work has broad implications, but certainly recently in healthcare and biological interactions, particularly in the use of nanoparticles for drug delivery. Luz is also active with the Society for the Advancement of Chicanos and Native Americans in Science, where she has been a member of the board and judge of engineering posters at their annual meeting. She's also a member of the National Society for Hispanic Physicists, where she has served on the board since '98 and was the president from '03 to '05. She is also a fellow of both the American Association for the Advancement of Science and also the American Physical Society. It is a great pleasure to welcome you back here, Luz. We look forward to your talk.
Okay, so I am giving this phrase, which was actually told to me by my advisor, whom Ben Ockel and John Hill, sorry, also share, the advisor. And I want to very, very briefly trace how I made my way from doing basic sciences to doing applications. So this is the other part of the title that appears in the poster that you already saw. So the outline of my talk, I'm going to talk about my support system. That's my family. I'm going to tell an aside because after Hurricane Maria, I have to give an aside to Hurricane Maria. Then I will discuss some research. I am sorry, Dune and Ben and John, it's not synchrotron work. But it is biological work, and things that can limit your work. So, how did I become a physicist? My support system. The first person I want to recognize here is my maternal grandmother. My maternal grandmother was a woman that only had a third grade education. She was pulled out at the turn of last century because they were very poor and they needed to work in whatever farm they were working. Her two older sisters didn't care that much about school, but she did. And she actually went to work. And but the idea of furthering her studies and stuff actually stayed with her. So she said that her children, my uncle and my mother, would continue up until the university. She was not going to get underway. So she worked even when she got sick to make them go to the university. And at that point, it was at a point where the Great Depression had ended and World War II had started. So there was a lot of need and a lot of poverty around. And people were saying, why don't you have your kids go to work? And she said, no, because my kids are going to the university. So my mother and my uncle went to the university, and that passed on from my grandmother to my mother. And I went to the university. So then my mother studied chemistry, and then she met my father, who was a chemist, and they encouraged me to go to science, into science. And then you might say, why did you go to physics? Well, I had a high school physics teacher, Don Leonardo Morales, who was a very good physics teacher. I say that because he did not start physics with, as you would commonly start it, with vector algebra, and if you have a vector that goes north, and you have a vector that goes west, where does the resultant vector go? He started with optics. And optics, then you had light and it was more visually attractive. So that actually hooked me up. So I wanted to study physics. My mother was happy with that. I don't think my father ever forgave me, at least. But he was also proud that I finished my career in chemist. So I had all of these people that were influencing me and giving me strength. And what they did was they helped me to know that I could do whatever I wanted, as long as I studied it. I wasn't going to come in here and talk to Duna and say, I want to do a synchrotron experiment without knowing anything about X-ray. And what I wanted was, I finished my BS and my BS and MS at the University of Puerto Rico, and my advisor was Don Fernando Diaz Colon, who is a doctor. So that's why I put the doctor, but we actually refer to them as Don. It's a way of respectfully addressing them. And then I went to do the PhD with Dr. Robert J. Bergeno, and that's where I started my work in liquid crystals. With Fernando, I worked on solid-state ferroelectrics, and these will come and join the two together in the work that I'm going to review for you. And then I also got the bachelor's in music and music performance from the Conservatory of Music of Puerto Rico. So what I learned in Puerto Rico was one thing that I actually found out that was not taught very well here in the United States. And it's because the United States has so many facilities and so many things. But actually, I learned that what you need is your brains to do work. And then you can go and do an experiment, and I know that everybody's going to jump at me, no, you need all the work, but if you don't have the materials, you can also go with your brains. And this brings me to my Maria side. This principal actually helped the University of Puerto Rico start classes in October 30th, 2017. That was 1 month and 10 days after Maria had hit. Pretty much most of the island was without power and without water. I always tell that the lack of water is more important than the lack of power. Because my friend and colleague and a cousin 8 times removed, it is indeed, we found that we had a common thing. So like it was said, we also include everybody, cousins. Actually, she teaches at the University of Puerto Rico in Humacao. That's in the eastern part of the island where Maria hit. And she had to teach her laboratory, her electronics laboratory. And she did it. And she finished in, with the electronics laboratory course, and until the electricity returned 2 weeks before Christmas, but that was when her course was almost done. So that is what I mean, that you have to use when there's nothing, you have to use your brains. So my field, as was said before by Dune, is the field of liquid crystals. And Dr. Virginal advised me, and I don't know if he advised John or Ben, but he told me when I finished that that I had to run as far away from what he did as I possibly could, because he was aware that women and or minorities were tied to whatever their work was, whereas men were not so tied to the work. And later up, he told me to never give up. That was more recently. So to run as far away from what he did implied that I could possibly not do any liquid crystals. But I was introduced to the liquid crystals that was described by Jen, which was a Nobel laureate, as beautiful and mysterious. And I was hooked in the liquid crystals. And you may say, well, you're cuckoo. But then I decided to go to the more applied route, since my advisor followed a more basic one, to establish myself. And then my postdoc at the University of Berkeley helped me on that path. Professor Ron was my advisor at the University of Berkeley. He is now retired, but he still has his office. I visit him. So several times I tried to do other things. I really did. I went to work with semiconductors. I went to work with some superconductors, or helped the research on superconductors by doing some X-ray work. But I always return to the liquid crystals. And I will be talking in about 2 slides, probably it's about 3 slides, because I added things. So things that I like about being a physicist, what I like is the interdisciplinary nature of my work. And I know that my colleagues will probably agree with me, that you get to know people from all over the world, and you get to talk about their ideas, and you get to go to wonderful places. And because it's interdisciplinary, that allowed me to actually move from physics into material science. Because in the words of my dean, who is an engineering dean, material science is the more basic science field of engineering. And I really don't know if he means that complimentary, but I kind of like it. So I told you that I meet people from all over the world, and I like to travel. Ben, I met with Ben and his wife last night, and they were asking me, what do you do for fun? So I travel. And I learned some languages. And also, I like to show my results, but not only my results, the results of other people as part of my class. And that has, it's advantageous if you teach a class that is not part of the core classes, because the core classes have a program that has to be met, because if not, the students won't be able to advance to the next one. But if you're teaching the courses that are not in that part, you can show some of your results as part of your class. And I can actually reach many more students other than the students that my money can allow to get for me, and inspire them to my course. Like this semester, I'm teaching the synchrotron course, and what I'm doing is I'm using the results from other people to get the people interested. Whether or not the students get interested, that's another thing. But I try to get them interested. And my activities, the other activities that I do, do actually mention some of them, but I have been a member of the APS Committee on Minorities, the APS Committee on the Status of Women in Physics, and the board member and former president of the NSHP. And I should actually say that I was the president twice. So I used to say I am the the once and future president. Is that the phrase used by King Arthur? I used to I am the once and future president. But I finally got out of the presidential line. And I'm a board member of SACNAS. So I was asked also for implicit bias, to talk to you about some of the implicit bias that I have encountered in my life as a physicist, and then as a physicist turned engineer. Okay, and bias nowadays is mostly expressed implicitly, but not explicitly. Although I may use some examples, that are not as implicit as they can be, and there are many examples where implicit bias will take time and energy that could otherwise be dedicated to my work as a physicist, my work as a material scientist, and your work. For example, and I didn't write it here, when I first started as a professor working professionally in science, I was in a department of electrical engineering, which the electrical engineering has some part of material science, so it looked natural. But I would go to a meeting of the different professors in different fields, and it didn't matter if they were in the administration or the higher levels of the faculty, or my colleagues at the same level as me. They would say, "Oh, you got here because you are a minority." And you do not know how much that influences how that conversation goes. That conversation goes nowhere. If you actually asked, "How did you get here?" I could probably say, "Well, I got here because I'm working with liquid crystals and I think it can help in some of the applications that you can." And you may or may not be interested, but you might say, "Oh, that's very interesting." Or if you are interested, it says, "That's interesting, tell me some more," and we can have an exchange. But telling me that I was a minority actually stops that. So it not only stops the conversation from going on, it stops me from meeting other people that might be able to contribute to my work, because they would say, "Well, I've heard about the liquid crystals, but I don't know what liquid crystals are, but I can use them," or "I don't think that it can be used in this application because of blah, blah, blah." It actually stops me from getting collaborators. Okay, it takes time. And when you hear it on and on again, and when you are not my age, you were a younger version of me, you get very frustrated. The other example I'm going to use is moved several years. Now I'm at Maryland, and I would say, "Oh, I'm a professor at Maryland." Because they would ask, "Well, what are you doing here?" I said, "Oh, I'm a professor at Maryland." The natural saying that you would probably say, "What do you do there?" The answer I got is, "Oh, you teach Spanish?" And I don't have anything wrong with Spanish professors, but I know that Spanish professors would probably not like me to be teaching Spanish. So there is an implicit bias that assumes that we all, just because we are Hispanic, we are going to teach only the language. We cannot teach any other of the disciplines. And believe me, in every single in every single Hispanic nation, as in this nation, you need everybody, from the high professors that do the research, to the engineers that apply the research, to the people that teach them how to speak. And I always have that tug of war with my students, because they say, "Oh, I don't need to know how to write English or speak English." I says, "Yes, you know. You need. I'm not going to teach you, but you need to learn that." Down all the way to people that clean your places of work. And believe me, if you teach at a university, you appreciate the people that clean your places of work. And that also takes time, because then you're wondering, there's no, you say, "No, I don't teach Spanish," but then where do you go from there? So the other thing that I have noticed is that many people either don't recognize it or don't see that. So what I'm telling you now is to be aware that would you want to have that question asked of you? Would you want them to also appreciate what you're doing? Where you start in the pecking order? So they don't recognize it, and then we are like, Cynthia was telling me this morning that a person here actually told that there was a brain where people could actually do physics all the time. Well, I kind of a little bit don't disagree, because they have family. But then you have the brain that you're thinking about, this person told me that I do this because I'm a minority, so I don't have brains to do this. Or these people think that I am teaching Spanish. So there's a lot of things that occupy your brains that shouldn't be occupying your brains. And as I said, when we are young, we actually swallow all of these things much more profoundly than we are. So, but along the way, I have another story. I have to get a prop here. This is a copy from Science Magazine from 2 weeks ago. If you go to the news, you will find out that a group of scientists has done a study and have found a gender gap in peer reviews. I know that I'm speaking as a Hispanic, but I cannot separate the fact that I'm a woman and a Hispanic. I'm sorry, but I cannot separate. And I'm pretty sure that if they did this also for Hispanics, because their last names are more easily traceable than other minorities, they would actually find that. And sometimes I feel it. This, I was feeling it in let's say, in my stomach, because how do I get so many rejections, and blah, blah, blah doesn't get that many rejections. But the reaction would have to be, "Oh no, you're fantasizing," but I have the proof here. So I don't have a solution to this, except to also use my advisor's word. His never give up actually had to do with his fight with physical review to actually get papers accepted. So never give up and actually go and fight and fight and fight. Except that I have given up in physical review. Sorry, but I do see this his view. And the final thing that I will say, that for 10 years, I was teaching 20 hours worth of courses No contact hours, just courses. Whereas the usual load for an engineering professor was 6 hours of courses in a week. So I tried to do it through all of the mediums, and I wrote nice letters, and I said, and this is the answer I got. Oh, you should think that you are now an English professor. English professors have to teach 5 hours of courses, or no, not 5 hours, like 20 hours of courses. Except that they actually teach a course several times, so they teach several different sections. And what is the problem there? The problem is not the English teacher, which I respect as much as the Spanish teacher. It's that I'm not an English teacher. So I was being put in a place that nobody else was being put just because they wanted me to be put there. So I don't know what the translation might be for this laboratory, but if a person approaches you with letters, and I think I wrote a nice letter because I had very good English and Spanish professors, so I think I can write a letter. And actually think about it, not tell them that you are complaining about, say, NSLS. You should actually think about what the nuclear physicists have to do. And I said, I do not work in the nuclear physics. I work in solid-state physics. Try to stay in the same area where you work, because it doesn't look well. And if you look around and you see that no, it's not happening to anybody, and again, like this last example, I don't know if it happened to me because I was a woman, if it happened to me because I was a Hispanic. I suspect that it happened to me because I was both. But that said, along the way, you shouldn't burn your bridges, because I got a AAAS fellowship. I did not need the backup of the head of my department or anybody in my department for that. But for the APS fellowship, they actually wanted to contact the head of the department. And he probably wrote a positive letter because I am an APS fellowship. And I also got the Edward Boucher Prize in Physics from APS. And the department chair had to give some input. So I think he did not put any negative input. And also, I got 2 Fulbright professor fellowships these were the ones that took me to Chile. They gave me money to be able to live there and eat there. The department chair had to give input on that. And it was required. They said, you have to have, I don't know, 2 or 3 people recommending you, including your department chair. So don't burn all your bridges, but just keep fighting. That's why I put this here. Because out of 4, I needed 3 for the department chair to actually say something about me. Okay, from basic sciences to applications, let's go back to science. I began my research work exploring basic concepts, phase transitions. I think Ben Alco was working also in phase transitions, and so did John Hill. Without any relation, or so I thought, to applications. But I think that we will all agree that that is not true. They are related in applications. And as I mentioned before, I went to do my postdoctoral work at Berkeley, and then I started thinking more on applications. And to do that, this facilitated me to get into an engineering department. But at the same time, I tend to say that decision gave the physicists the right to look down at me because I was doing too applied work, and the engineers to look down at me too because I was doing too basic work. That's why I've given up on physical review letters. So that can give me the set of the little work that I'm going to illustrate that has to do with biosciences. But I have to go back there. I have to go back 12 years. And those 12 years were at the time when I was recovering from going to the NSLS. So these are, I'm sorry, these are not synchrotron papers. But we wrote several papers related to that. And they had to do with the effect of the surface coating on these nanoparticles. On the surface coating of a nanoparticle that was magnetic on the magnetic liquid crystal interaction. And just to be very quick, this black dots are when I did not apply a field, and these other dots were when I applied a field. And the field was very small. It was just 362 millitesla. If you remember, we actually needed that very large magnetic field that was like 1 Tesla or 4 Tesla to align this. So you put these little particles, and they align this. Okay. So we wrote several papers. And the nice thing is that I'm pointing out this person got the person in purple got master's with me. The persons in red were undergraduate students working with me. Those were the undergraduate students that I couldn't bring over to the NSLS because they had other things to do. It's very difficult to actually bring another student to the NSLS. And L.K. Kurihara was my chemist collaborator. She was the one that fabricated these nanoparticles. So the one thing that was important to it was that we were working with asmectic. That just means an ordered phase of the liquid crystal, rather than the regular nematic phase, because if you look, there were many, many papers working on the nematic phase. And then you're looking at me and saying, yeah, but what does nematic and smectic mean? I think I have, oops. This is a review. We found out how the liquid crystal reacted to magnetic nanoparticles. And as I said, this was a result that started looking at how cells, living cells, reacted to the nanoparticles. And we suggested that this liquid crystal nanocomposite could be used for biological application, and that was the end of it, 2009. And it stopped there. But then a former student suggested that my group could help out Dr. Weinstein, who is a PhD in physics and an MD. And Dr. Mayer, who is a doctor in material science, but they have a small company, to find an appropriate material for their new contrast agent. And this is more for the students, so I'm going to skip it. Before I go on, what is a liquid crystal? Except for the people here. Anybody knows what is a liquid crystal? Well, a liquid crystal, you can imagine it like being an ellipsoid. So it's not like a ball. So it has a, it is a, it has different, different ways of relating to each of the other ellipsoids. And these are some of the faces that you can get. So I mentioned you the smectic A, which appears here, where all the ellipsoids are looking up to the top of the ceiling. And if you look at it here, sorry. If you look here, they are subdivided into layers, okay? But they can also be at an angle to those layers. So those are called the smectic A and the smectic C. And like I tell my students, there is a verifiable alphabet soup. So those are not the only two faces. And here is the other face, the other common face, which all the ellipsoids are pointing upwards, but they don't have any I'm afraid to actually point this out. This doesn't point any. Well, anyway, they don't have any layer that separates them. So what separated our work from the other work was that we were doing it in the smectic phase. And most of the work was dedicated, most of the work and most of the theoretical work was dedicated to the nematic phase. And here is the ferroelectric phase. And for the physicists, ferroelectric phase actually means that you are substituting one of the, or actually for the chemist, you're substituting one of the hydrogen bonds with something else. But you don't need any other thing if you're not. And like the liquid, like the solids, they have structure because I just described it. They have some structure. But like liquids, they can still flow. So that's why they are known as liquid crystals. Okay. So what is a nanocomposite? Any combination of two or more materials that has different properties, and you use them in combination to obtain a third material that combines the properties of both and probably brings the properties of both to a better application. So what we were doing is combining liquid crystals, which are organic particles, with nanoparticles that are inorganic materials. And we have combined them either with magnetic materials or semiconductor material, but I'm going to stay with the magnetic material because this is the work that Dr. Weinstein and Dr. Mayer, which were some of my collaborators, and I'm listing my collaborators too. These are my collaborators from the University of Chile, in Santiago, Chile, and again, my collaborator from, which she's now working at NextFed. What they were asking was that the nerves in the body send electrical signals. So the nerves in your body are like something that sends electrical signals. However, these electrical signals tend to be fairly weak, in the order of 20 volts per meter. So what Dr. Weinstein wanted to do was actually find out if there was a way, if there was a mixture of liquid crystals and magnetic nanoparticles where the LC will be aligned by an electric field of this amplitude. And once they're aligned, because once you align the liquid crystal, you also align the magnetic nanoparticles. Will this create a magnetic field? Okay, so, and they want to use it in our brains. This is their concept. But they have been trying some of their ideas on mice. And the arrow actually points out where they have the liquid crystal. It's of course it is contained in it's not free. It's contained in a like you would have you would get your medicine. So I will get this right when it's done. So these were the previous results that I was shown, and I added this after I had added it before. So we had shown it for the smectic phase, but my idea was that probably we could also use it with a ferroelectric phase. Why? Because the ferroelectric phase has one thing that the smectic phase will not do, and that is a vector that we call the polarization vector that will interact with the electric field and align the electric field. I mean, align the liquid crystal and align the nanoparticles. Okay, and we tried it. This is you might actually associate this with the pictures that they so artfully distributed in the announcement for my talk. But what I was showing here was that if I went from 50 volts to 100 volts, there was a change. And 50 volts to 100 volts is a lot. But we were trying this in the smectic A phase to actually see that we were seeing something. And what we actually saw, the applied voltage. If it increases the applied voltage, you would increase the order of the liquid crystals. And hence, you will actually get a signal with the with a signal measured with the magnetic measurement. Okay, so we have proved that, except that this had too much of a concentration of nanoparticles and too high of an electric field. So, and since I'm running out of time, this was the materials used, and the nanomaterials used. I should emphasize that this is a model system, so don't try this in your brains. And what we found out was that if we have these nanoparticles, the nanoparticles actually tend to cluster themselves. And then if you go from a disordered to an ordered liquid crystal phase, they actually tend to cluster inside these little spherulites. I'm sorry, inside these little spherulites. And we found out that we actually found out the same thing with the ferroelectric liquid crystal. So we could actually test them. And that's where my friends in Chile, who are experts in ferroelectric liquid crystals, which I'm not, actually tested it. And this is an exaggerated thing, but you can see over here in the center that it gets more and more ordered the higher the electric field you apply. And it actually gets more ordered at lower electric fields. I'm using this because you can actually see it. So we studied the effects of an applied electric field, and we actually showed that you can actually get a magnetic field. And this is actually used in a magnetic field that can be read by an MRI. So that's the application that's used. That's the biological application that's used. So I hope I showed you that how I became a physicist. And I reviewed some of the implicit biases I have found. And I went over one of my research programs that resulted in an application many years after I had finished, or the funding had forced us to finish our project. So my message is never give up, because it will come, if it's good work, it will come back to you. Thank you. Oh, I wanted to show you, this is what I did last year. I did my 6 months of work in Chile. It was in the winter in Chile. These were my 5 collaborators. I'm saying 5 collaborators because this lady here was expecting, and she had a little girl after she left. And I was able, that's my view from the front of my apartment. So I got back home and I would always see this. And then at the end of the semester, I took a week to actually go down south to Punta Arenas, and I'm a person from the Caribbean. So going to Punta Arenas was something special for me. And I got to see the penguins, and I got to dip my hands in the Magallanes Strait. That actually seemed a construct of history, but actually to see it, it was very exciting. And that picture was taken by 2 people that actually went into the dip of the Magallanes Strait, which is the equivalent of the polar bear dip. So I was there with three layers of clothing, and they were there with just a bag. Anyway, thank you. Hi, Ken.
So the very younger ones, you mentioned that sometimes the implicit bias leads to loss of time on your part, some sort of emotional waste, energy wasted. And so, what would you recommend for the younger ones how to handle that situation so they don't get distracted?
I hope that they can listen not only to me but to other people. And to fight with people that actually say you got this as a minority, and I said, and actually answer to them, no. I went on a competition, and I won this because I was really prepared, and this is my work. I had known that because I was flabbergasted. So I wish they were more. I hope I can teach them to actually be more valiant, more assertive than I was. So actually to say, no, I did not get this because I was a minority. I got this because I competed for this. And yes, there are some programs. There are less and less that are dedicated to the minorities, but they are not like, I walked out of the street and I said, I want this prize, and they gave it to me. Like Ken will actually agree with me. That is not the way it's done. So it's done in a competitive manner. And one thing also, if you are looking at projects, also get the, I know it's a very small cut of the population, but you can always choose the best people from that small cut. And the best people are as good as the other people. So it's me and us, me and them. As the other people, and then just choose them. Because I've seen people say, oh, this is for minorities, let's grab any minority. And then when they fail, they say, you see, they didn't work out. That's because you made a bad choice. It wasn't because they applied and they were giving it, was because the person that was choosing them did a bad choice. And then the project was, I had a page that I did not do that was dedicated to the students, because students and this applies to all students. Students say, well, if you don't get this immediately and it doesn't go up to any application immediately, then you will never get it. And that's not true. Oops. Okay.